Very happy to be here to talk to you about kind of a smattering of work that I've done both at UNC and at Huggingface over the last, let's say, year or so, trying to reevaluate the way that we build language models. And I think I haven't given this talk before. This is a new set of slides, so I think it should not definitely be, it should definitely be less than an hour of talking. And I'm happy to make this as discussion based as possible. I tried to kind of string together things in a coherent way, but there's a lot of kind of ways to take a different path through this work or discuss other work that I maybe did or did not include. So feel free to stop me with questions, either by hollering out or some other way, but otherwise happy to have some discussion at the end. So maybe to motivate this talk, I'll just start by clarifying for me personally why language models are useful, why they're an exciting paradigm. And maybe at risk of overclaiming or stating the obvious, I'm going to present you with 3 paradigms for building software that understands language in some way. And the first paradigm is basically the traditional paradigm of writing software, writing down where we basically write down a set of rules, a specific program for what we want the software to do. It's basically a hand-designed program. And in the context of natural language processing, the way that we might build such a system, for example, let's say for sentiment analysis, is by first writing down for each word what the sentiment of that word usually is. Okay, and actually people have done this, and this is an example from the text blob library, although I think this came from a different library called Pattern, and even then I don't think the library itself was the original source of these annotations, but at any rate, this is basically a big dictionary, and for each word in the dictionary, like the word appalling being shown here, there are various annotations describing properties of that word, including the polarity. The polarity there is the 6th line down, and the polarity basically is a number between -1 and 1, and it specifies how positive or negative the word is. -1 is very positive, 1 is very -1 is very negative, 1 is very positive. Also, the subjectivity and intensity. These were annotations written down by someone at some point. And if you take such a dictionary, you can write a chunk of code that looks something like this, basically iterating over a list of words in a sentence or a document, and looking for known words, and basically just writing down their polarity. If the word is not known, or excuse me, if the word is not known, you skip it. But if the word is preceded by a modifier, like really, a few lines down, then you modify the polarity in kind of a heuristic way, a hand-designed way. And if the word is preceded by a negation, like not, then you also change the polarity. And so what this does is ultimately you have a kind of, well, let's just say a heuristic, rule-based, hand-coded way of coming up with the polarity of each word in a sentence. And then if you want to know the polarity of the entire sentence, you just compute the average at the end, the average of the polarity of the individual words. Okay. And so it turns out this works okay for a simple task like sentiment analysis. And this is kind of how software has been built for forever, right? If we want our computer to do something, we write down the steps that should be taken for it to perform that task. And then we hope that the computer does a reasonable job at performing the task. Okay, so this is kind of traditional software development. Now, an alternative paradigm is machine learning, of course, right? Where instead of writing down the steps that we want the computer to take in order to do something, we actually just show the computer a bunch of examples of what we want it to do, and then train a model to basically make decisions to produce the output of the program based on the examples we provided. So here's a very abstract representation of, let's say, classification, where maybe we have represented sentences in some way in a 2-dimensional space, so that we can basically draw a line through that space and separate out the positive versus negative sentences. Maybe positive is orange and negative is green. Okay, so in this case, we need to come up with some way of taking the sentences and mapping them to the space where we're going to perform classification, but there are lots of ways of doing that. And it turns out that this works reasonably well. The key thing that this requires is a way of mapping from text to a space where we can perform classification. It's either called feature engineering or representation learning or something like that. It also requires a training set, right? We need a set of data points that are annotated with the label that we want the model to predict. Okay, so this is a way of, rather than writing down the steps that we want the computer to take to do the thing we want, just providing examples of what we want the computer to do and allowing the computer to learn its behavior. Okay, machine learning obviously works well in a lot of cases, especially when you have a lot of these annotated examples. Okay, so this is kind of paradigm number 2. Now, paradigm number 3, of course, is a language model. And so why do I think this is a different paradigm? Well, it's because rather than hand coding the things that we want, the thing that we want the computer to do, or showing the computer lots of examples of what we want the computer to do, we just ask the computer to do what we want in natural language, and then hopefully hope that it does. Okay, so for example, this is a diagram that we'll return to in a little bit, but the basic idea is that I have one system where I can feed in some text that I want to be analyzed, and then maybe a question about the text or a request for the language model to perform some particular task. And then I look at the language model's output, and the language model hopefully will have output something that completes the task. So we might be able to do this for summarization. We feed in a document. We ask, how would you rephrase that in a few words? The language model then outputs a summary of the document, for example, on the top. And we can do this for generative tasks. We can do it for classification tasks. But again, the key thing here is that rather than writing down the rules or providing examples, we're just specifying the intended behavior in natural language, which is arguably a more natural way of interacting with a computer or really any agent, right? Because it's the way that we interact with each other. If I wanted you to summarize a document, I might give you the document and ask you, how would you rephrase that in a few words, okay? So I do think that this is a promising approach to a new paradigm for getting computers to do what you want. So now, with that in mind, I will talk about the ways that people currently build language models and some work that suggests better ways to build language models to achieve this goal, namely basically instruction following, where the instructions are in natural language. Okay, so how are most language models built, at least this kind of language model? Well, the first thing we do is we go and we collect a bunch of text. Usually we scrape the web and get a bunch of text from the web. And then in the dominant paradigm, we train a language model to predict basically a continuation conditioned on a prefix. And this slide is maybe not the most reliable representation of that, but in most cases, as I'm sure you all learned in this class or already knew, when we train a language model to do this, we are essentially training it to predict the next word or the next token in a sequence of text or a sequence of tokens over this entire pre-training corpus. And again, this pre-training corpus is usually just a big dump of text that we collected from somewhere, usually from the web, okay? And the hope is that if the language model is good at predicting the next word, and we feed in, let's say, a question on the right here, like suppose the banker contacted the professors and the athlete, can we infer the banker contacted the professors? The language model has learned that usually when you see a question, the question is followed by an answer, and maybe it has seen enough questions that it has kind of general question answering capabilities, so it appropriately predicts that the next word in this case is yes, okay? And therefore this model would perform this task, the natural language inference task, in what we call a zero-shot way. And we call it zero-shot because we never intentionally trained the model to perform this task. We just trained it to predict the next word or the next token over a large collection of text that was not intentionally human annotated, okay? So we call this zero-shot learning because, again, the model was not intentionally trained to do this. And we call it prompting because we've prompted the language model to do what we want. And it turns out that if you build a language model in this way, and it was really the GPT-3 paper, the paper list on the bottom of the screen that drove home the effectiveness of this approach. But if you build a language model in this way, you train a language model to predict the next word or the next token in a giant corpus of unstructured text, then the language model can actually perform many tasks in this zero-shot way. You ask the language model to do something, and it does a reasonable job of performing the task. So here is the accuracy on a question answering benchmark called Trivia QA that we'll return to a couple times in this talk. But in Trivia QA, the basic idea is that there is a question, and it's a question about a factoid, a kind of a trivia fact, a kind of a possibly well-known fact about the world or about a well-known person or something. And we're evaluating the language model on its ability to answer the question correctly, okay? And I won't get into a lot of details on how this is actually evaluated, but the important bit in this plot, which should come as no surprise to any of you, is that as we scale the model up, the performance on this task gets better and better. So larger models tend to be better at least this task and many other tasks. And I haven't actually shown it on this plot, but you might be looking at this and thinking, oh, 60% accuracy or 70% accuracy, that's not that good. But a lot of these questions are kind of ambiguous. And if you feed the model the question with no other context, it can be a little hard to figure out what the correct answer is. And there's lots of different ways to paraphrase an answer. So human performance on this benchmark is only about 80%, okay? So it's actually not far from human performance. And again, this behavior kind of emerged from just training the language model to predict the next word in a large collection of text. And that's kind of interesting. So now let's think about whether this paradigm of training a language model to predict the next word in a big collection of text is the most effective way to produce this behavior. And so now I'll motivate an alternative paradigm, which maybe won't be too surprising to you. I think this is more common now than it used to be. An alternative paradigm for getting language models to do what we want. And to motivate that, I'll first note that many of the things that we want a language model to do, these tasks kind of appear implicitly in the large text corpora that we train them on, these web scrapes, let's say. So going back to the example from the previous slide, this question answering task, where you just feed the model a question and see whether it predicts the answer correctly. Here's an example of one web page on the internet that has just a list of a bunch of questions and their answers. So for example, who is Frank Sinatra, ? Answer, an American singer, actor, and producer, okay? So this is very similar to the format of the task that we just evaluated GPT-3 on. And this kind of text appears all over the place on the internet. There are lots of pages with trivia questions on them. So in a sense, if we train on a bunch of text from the internet, and we assume that we're going to hit some of this text somewhere, we actually have trained the language model to perform this task in a supervised way. So calling it unsupervised is maybe a little misleading, but we might say that we did not intentionally supervise the language model on this task, okay? And there are other examples of task-like data on the internet. For example, for paraphrase identification, do these sentences mean the same? I should say same thing, but this is a copy verbatim from someone who doesn't know perfect grammar. But anyways, do these sentences mean the same? No other boy in this class is as smart as the boy. No other boy is as smart as the boy in the class. So this is a classic natural language processing task, paraphrase identification. Do these two sentences mean the same thing? Same with natural language inference, summarization, the example I gave a little earlier, even pronoun resolution. So it might actually be the case that a lot of the instruction following capabilities, a lot of the abilities of language models to perform these tasks might come from the fact that there's a lot of unintentionally collected supervised data for these tasks in the corpora that we train them on. So if that's true, then the idea is maybe we can do better by intentionally training a language model to perform all of these tasks. Okay, so for example, and we might pick a bunch of NLP data sets and convert them to a instruction-like form. So we're the format that I was describing a few slides ago, where we feed in the text that we want it to be analyzed, we feed in the request, the instruction, and then we train the model to predict the correct answer. And if we do this on enough natural language processing data sets, and we produce diverse enough prompts, then maybe after we do this form of multitask training, we call it multitask prompted training on a language model, then we can feed in a new task via a new prompt and a new example, and the language model will perform that task correctly. And the key question here is, does this multitask prompted training step produce a model that has better zero-shot performance on a wide diversity of tasks than a language model trained in kind of the typical traditional way, where you just train it to predict the next word over a corpus of unstructured text. Okay, and if it does, then that might suggest that actually this kind of data is much more valuable for inducing this behavior. And again, a year ago, this idea was kind of weird. Now I think people have done this kind of thing enough that maybe this doesn't seem that surprising or unusual. But at any rate, let's talk through. So in order to answer this question, we went out and grabbed a bunch of NLP data sets. Fortunately, there are a lot of them out there. And we categorize them into different tasks, because again, we want to know how well does the language model generalize to unseen tasks, not unseen data sets, right? If you think of a data set as a collection of text that falls under some particular task, maybe that has some domain, some language, then we actually want to measure task level generalization. We want to measure generalization to new capabilities that the model was never intentionally trained on, okay? So in our case, we separated out tasks into multitask training categories and held out categories. Shown the trained on categories are shown in yellow and blue, and the held out categories are shown in green. And so you can see that we're ultimately going to be testing the language model on a diverse set of capabilities like natural language inference, story completion, word sense disambiguation, and co-reference resolution. Okay, so now we've chosen our data sets. We've kind of segmented them into held in tasks, held in capabilities, and held out tasks. So now what do we need to do? Well, we need to convert these data sets into that kind of instruction-based form. So how do we do that? Well, we just kind of crowdsourced it. We solicited a bunch of volunteers, as Daniel and his collaborators have done for natural instructions, especially natural instructions v2 or supernatural instructions. And we just asked people to write prompts, and we prioritized writing multiple prompts per data set and also trying to write diverse prompts that had differing formats. So for example, for this question paraphrasing data set QQP, where the goal is to predict whether two questions are asking the same thing, here are two of the prompts that were written of many. One of them, for example, says, take question one and concatenate it with question two, and then it says pick one, these questions are duplicates or not duplicates, and then the prediction is the choices array, which is well, it would probably then say duplicates and not duplicates indexed by the label. So hopefully that syntax makes sense here. And you can do the same thing for a summarization task. And we got about 40 people to help us write these prompts for all the data sets, and ultimately collected, I think, 1,700 prompts for over 100 data sets. Okay, so then what happens if we take a pre-trained language model, in this case T5, which I think you all have been exposed to, so I won't talk about it too much, and we do multitask prompted fine-tuning. So we take all of those data sets that we prompted and we fine-tune T5 on those data sets, and then we evaluate the performance on the zero-shot tasks, the held-out tasks. And what we found was that for many data sets and therefore many tasks, T0, which with 11 billion parameters, a fine-tuned variant of the largest T5 variant, actually outperformed the largest GPT-3 model in the zero-shot case. Okay, and that was true actually across all of the natural language inference data sets we considered over arguably one of the co-reference resolution data sets, some of the sentence completion data sets, and in the word sense disambiguation data set. So it's not true that in every possible case T0 outperformed GPT-3, but it was true in a lot of cases. And to me, this really drives the point home that if you want a model that performs zero-shot generalization, that follows instructions well, this approach where you intentionally train the model to do to follow instructions and to complete requests will produce a model that generalizes better to new tasks than the standard, training on unstructured text with a next step prediction objective. Okay. And of course, this is somewhat limited in the sense that we only considered these tasks, at least in this diagram, but we also evaluated the models on a subset of Big Bench, which intends to test a really diverse range of tasks and saw similar behavior where the performance was typically about as good or better as much larger language models trained in a standard way.
I have a question. So, did you find any degradation in performance in some other tasks that GPT might still be good at?
Yeah, so the paper that we tested the degradation in performance on other tasks is the paper I'm going to talk about in just a second, but I didn't include those results in the slides, so I'll try to mention them again. I'll try to answer your question in a couple of slides, even though I don't actually have that content in this slide deck. Yeah. Okay, so at least preliminary results suggesting this is a good way to get language models to do what you want. So now I'll talk about the paper I just alluded to, where we were interested to see not only if we could get zero-shot generalization to new tasks, but also if we could get cross-lingual generalization. So namely, if we took a multilingual language model, a language model that's pre-trained on text, not just in English, in many, many languages, and then we did multitask prompted training on English and non-English data sets. Could we get the model to perform a given task in a language that it was never explicitly trained on? And in particular, there's kind of two kinds of generalization we might hope for. One is, will the model perform a task that it was trained on in one language in a different language? And second, will the model be able to perform a task that it wasn't trained on in any language, but it was pre-trained on? And so we built three variants of P3, which is the collection of prompted data sets we built for the prior work for T0, and the two additional variants that we built either just created templates for multilingual data sets or created prompts that were not in English. Okay, that's shown on the right there. So we also would hope that if we have a multilingual model, we could ask it, we could make our requests not in English. And the only result I'm going to highlight from this paper right now, even though there's a lot of other interesting results there, like the one that was just asked about a moment ago, is that we considered applying multitask prompted fine-tuning to basically two models. One was MT5, which was a multilingual variant of T5 pre-trained on hundreds of languages, and Bloom. Bloom is a large-scale multilingual language model that overall has a similar architecture and training objective to the GPT class of models. Okay, and again, the only result I'm going to highlight here from this paper, which maybe I should have included more stuff from here, but anyways, the only result I'm going to highlight here is that interestingly, MT0 actually, which is the multitask prompted fine-tuned variant of the largest MT5 variant, outperformed the multitask prompt fine-tuned variant of Bloom. And that is despite the fact that Bloom is a model that's 16 times larger. So in both cases, we saw, or at least I should say, when going from the original Bloom to the multitask trained Bloom Z, we saw a big boost in performance. That's from dark blue to this kind of burgundy color. But still, MT0 was a lot better. And I'll talk about that result in a little bit more in a second. But first, I want to not forget the question that was asked a minute ago. So one thing that we tested here was whether multitask, so I should say, when going from T5 to T0, like we did in the work I just spoke about a moment ago, we couldn't really test whether the model's zero-shot capabilities degraded, because T5 is not really an appropriate model for zero-shot task generalization because it was trained with a masked language modeling objective. You can kind of force, and I'll talk about one way to do this in a minute, you can kind of force T5 to do, to follow instructions in some ways, for example, by, masking out some of the tokens and having it fill in those tokens. But in the true sense of just being able to ask it to do something and generate a bunch of text that hopefully does that thing, T5 is not appropriate for that. So we couldn't test the question that you were asking, but we could test the question with Bloom and BloomZ, the original language, the original next step prediction language model Bloom, and BloomZ, the multitask fine-tuned version, because Bloom actually does have some instruction following capabilities because it's just a model to predict that's trained to predict the next token. And what we found, as maybe you would suspect, is that the distribution of tasks that we trained on impacted, basically got better at tasks and data sets that kind of had the same general flavor to those that were those that it was multitask trained on, but it also got worse at other things. And one very concrete example of this is that most of the data sets that we fine-tuned Bloom on were classification data sets, or at the very least, they were very short form generation data sets. So if we're doing kind of long form generation, more like abstract tasks, Bloomz ended up degrading a good bit. And one example, the difficult thing about these long form generation tasks is that they're very hard to evaluate. But one example of a task that actually has a meaningful way of evaluation is basically code generation tasks, where the model's asked to write some code that does some particular thing and is evaluated on whether the code actually does the thing it was asked to do. And what we found is that the more that we did the multitask fine-tuning on Bloom, the worse it got at that particular task. Now, what we did to get around this is we basically just didn't fine-tune it for that long. We fine-tuned it for long enough that the performance got better, and maybe didn't maximize the performance on classification-like tasks, but we didn't fine-tune it so long that the performance got dramatically worse on long-form generation tasks. And to me, it's kind of a it's kind of a classic generalization, machine learning style generalization question, right? Like, these models can generalize to new things that they haven't seen before, but the closer the stuff that you train on is to the things that you want to generalize to, the better it will generalize. And I'm happy to talk about that point more later. Maybe we're in more free-form discussion, but for now, that's kind of one point in that favor. And actually, another point in this favor that I wasn't planning on mentioning, but now that I'm just on this huge tangent, I'll mention it quickly. One of the models in this plot is MTK, which came from the Supernatural Instructions paper that I mentioned earlier. And MTK surprisingly doesn't perform particularly well on these data sets. And even though it's a very powerful model that performs well in a lot of cases. And similarly, in the paper that MTK came from, the Supernatural Instructions paper, T0 performs pretty poorly on the prompts and data sets they consider. And really the main difference here, I mean, these are two, MTK and MT0 are two models that were created in the same way via multitask prompted training, basically. The difference is the prompting format. So MT0 and Bloomz were trained on P3 and XP3 that I mentioned a second ago, which use a prompting format that basically targets zero-shot generalization, where I just ask the model to do something and it does it. MTK is trained on typically on a two-shot for a prompted format, where the model is provided with two examples before it's asked to perform the task. And also the kind of type of prompts that MTK was trained on and the type of prompts MT0 was trained on are quite different. So, but what we find is that MT0 or T0 specifically does poorly in the supernatural instruction setting, and TK or MTK performs poorly in the P3 setting. And what this suggests is that these models are actually generalizing, but only in a limited sense, only to prompting formats that look like the stuff they were trained on. So kind of just an interesting side result there. So great. Now the question is, why does MT0 outperform Bloomz? Why does a model that went through the same multitask prompted fine-tuning step that is much smaller outperform Bloomz? So to answer that question, we had another paper. Oh, actually, no, let me, I forgot. I was going to also mention this result. So this is a result from the Flan paper, which came out right around the same time as T0. And in the Flan paper, they took a decoder-only language model trained for next step prediction, much like Bloom, and they fine-tuned it via multitask prompted training. They call it instruction tuning. And one interesting thing that they found was that the model's capabilities to zero-shot generalize to new tasks only became beneficial at a certain scale. So if a model was too small, you look on the kind of on the left side of this x-axis, the blue line, which is the model's performance on zero-shot generalization after multitask prompted fine-tuning, was actually worse than the original model. So doing multitask prompted fine-tuning actually made the model worse. And they only saw gains from doing multitask prompted fine-tuning when the model was sufficiently large. And this is weird because T0 and MT0 are right about at this point on the curve or on the x-axis where they don't see benefits, or maybe they see a very small amount of benefit, okay? So this is weird, right? It kind of asks the same question. What is it about T0 and MT0 that produces so much better models than the Flan model and from Bloom Z? Okay, so to answer this question, we undertook a study of what language modeling architecture and pre-training objective produces the best zero-shot generalization, either with or without multitask fine-tuning. Okay, and the key thing that we're highlighting here is that the difference between Bloom and T5, for example, as base models for multitask fine-tuning is that Bloom was trained for next step prediction via like a causal, what we call like a full language modeling objective with a causal decoder architecture. Whereas T5 has a completely different model architecture. It's an encoder decoder model trained on a masked language modeling objective where it's trying to fill in blanks in a synthetically corrupted input text, okay? And the question here then is, as we undertake this big study, will we confirm that, for example, in a controlled experimental setting, that, for example, a causal decoder model trained with full language modeling, like Bloom or the model underlying Flan, will perform worse after multitask fine-tuning than, let's say, an encoder decoder model trained with masked language modeling. And the reason that we undertook this study is because, you know, Bloom, there's a lot of differences beyond just the architecture and the objective between, for example, Bloom and MT5, for example, the scale, the data that it was trained on, and so on. So let me just kind of highlight these architecture and objective differences that I was mentioning, just to make it hopefully totally clear. The first is basically what tokens does which part of the model architecture have visibility to when it's making its predictions. So at the top left here, we have the standard setting. This is the GPT style model, where you have what we would just call like a decoder stack that always has causal visibility on its input. And what that means is that when it's predicting the next token, it can only see previous tokens. An alternative to that is not very widely used, but does exist, is what we call a non-causal decoder model. It's also been called like a prefix language model. And in that type of model, we modify the attention mask in the transformer layer stack so that it has full visibility over what we would call like a prefix. You know, in the case of instruction following, the text that we want to process and the instruction, there's no reason to not give the model full visibility of that region of the input. We only want to force it to have a causal visibility once it starts predicting the output. Okay, so the non-causal decoder kind of gives a balance between those two things. And then the last model architecture we consider is the encoder decoder model, where rather than having a single layer stack, we have two layer stacks: the encoder, which has full visibility over the input, and the decoder, which generates the output one step at a time. And so the encoder decoder model is kind of the original architecture for the transformer, but the causal decoder model is what people typically use to train models like the GPT class of models. And so on the bottom, I'm highlighting the different objectives that we tried. Full language modeling basically means that we are going to train the model to predict every token in a chunk of text, one token at a time. Prefix language modeling means that we're going to provide a prefix to the model, and then we're going to only train the model to produce a continuation from that prefix. And finally, in mass language modeling, we choose random spans from the input, drop them out, and train the model to predict the missing spans. Okay, so that's kind of what was done in T5 and BERT and many other models. So then the question becomes, which combinations of these architectures and objective produce the best zero-shot generalization capabilities with or without multitask fine-tuning? So here are the results, and this is a big empirical work, so there's kind of a lot to parse here, but I'll try to give a quick overview of it. So first of all, the blue line shows random performance on 2 evaluation suites. One is evaluating on the tasks that were held out from T0 that I mentioned earlier, and another is on the Eleuther AI evaluation harness, which is a piece of software that's designed to test models in the same setting that GPT-3 was tested and evaluated. Okay, so we considered 3 baselines shown on the left, and in this case, we're contrasting these baselines with what happens after multitask prompted fine-tuning. The first baseline shown in black is what people call LM adapted T5. So if you take T5 and then you do continued training on a prefix language modeling objective, you get T5 plus LM or LM adapted T5. It's not a very good language model. It's just kind of a simple baseline to compare to. The second point, the gray point, is T0, literally. The third point is a causal decoder model trained with full language modeling for basically the full amount of training that we're going to be comparing to for these other models. And you can see that, interestingly, actually on the T0 eval, the kind of average performance is basically at random for the causal decoder with full language modeling. And one reason that could be is that this model is maybe not big enough to perform really good zero-shot generalization without any form of multitask fine-tuning. So now we compare it to 6 variants, basically exploring different pre-training objectives, different architectures, followed by different kinds of multitask fine-tuning, okay? And so the syntax here, if you're trying to read the caption, is that the first 2 letters before the colon refer to the architecture, like CD for causal decoder, for example, and the 3 characters after the colon refer to the type of training that was performed. So one thing I'll just quickly point out is that if you look at the pink dots, the causal decoder model trained with full language modeling, if you take that model and perform multitask fine-tuning, it significantly outperforms the pink circle and the baseline model. Okay, so in both cases, you get a big boost from doing multitask fine-tuning on the causal decoder model. But notably, that boost is not big enough to catch up with kind of the T0 style training, which is shown in dark blue. And so, for example, if you look on the T0 eval, we confirm that by using an encoder-decoder model and training with mass language modeling, and then performing multitask fine-tuning, we get a model that performs about as well as T0, let's say. And one notable issue here, or problem, is that if you, instead of using a mass language model pre-training, if you use a prefix language model pre-training to get the light blue point, that actually performs dramatically worse, okay? So now we're kind of in this tricky situation where if we train a causal decoder model with full language modeling, at least on Eleuther AI eval, it works okay. But if we want a model that performs as good as possible, it seems like we should do mass language model training. And in particular, we should use an encoder-decoder model. So there's kind of no best of both worlds. Like if you're targeting doing multitask fine-tuning eventually, it does seem to be best in both settings to train an encoder-decoder model with mass language modeling. But if you want a model that works well out of the box and maybe works well on tasks that aren't well evaluated in these 2 settings, like we mentioned a minute ago, then you need to train a model with some kind of full language modeling or prefix language modeling objective, but that generally produces worse performance. So then we explored ways to kind of adapt a model trained in one way to a different setting, a model trained in a different way. So one thing we tried was taking a causal decoder model trained with full language modeling, kind of the standard GPT recipe, and then trained it as a non-causal decoder model with mass language modeling. Or excuse me, that was backwards. We took a non-causal mass language model and we adapted it via a standard full language modeling loss. And that's shown on the left there. And you can see that if you look at the performance after adaptation, you can get an equally good model for causal full language modeling objective more quickly if you start from a pre-trained non-causal mass language model, although the speed up is not that high. On the right, we're comparing training a causal mass language model to a non-causal mass language model in blue and orange, and then taking a causal decoder model trained with full language modeling and adapting it via mass language modeling. Okay. So in this case, we actually see a much bigger speed up. So basically, if we took the blue model and we trained it for just a little bit extra time as via a mass language modeling loss, then it matches the performance relatively quickly. We get like a 9x speed up in terms of how quickly it converges to its solution. And we get about a 3.3 times speed up compared to the non-causal mass language model. So these adaptation results provide some way of getting the best of both worlds. And a very similar recipe was used recently for in the UPalm paper, if anyone was familiar with that. So I don't know why this figure isn't showing up. Let's see if I can get it to show up. Yeah, let's see, it's going to show up now. Nope. Can you all still see my screen? Maybe I'll just show it to you here.
Yes, we can.
Yeah, okay, great. So so far I've been focusing on zero-shot generalization, but zero-shot generalization is not the only way to get language models to do what you want. As I mentioned when I was discussing the MTK results, sometimes when people try to get language models to do new things, they feed some examples into the language model of the desired behavior. Okay. And so this is a figure from the GPT-3 paper where they're contrasting 3 different paradigms for getting language models to do new things. In the first, at the top left, is what we've mostly been talking about so far, where there's kind of some instructions and an input, and the model is asked to just produce the output in a zero-shot fashion. That's being contrasted here with fine-tuning, where we feed the model input-output pairs and update its parameters in order to get it to perform the task hopefully better and better and better. But in the GPT-3 paper, one of the main innovations was this idea that if you put input-output examples just into the context, into the model's input, when you're asking it to do something new, excuse me, it's a way of making use of labeled examples that doesn't involve training. And in particular, adding these examples in context tends to improve the performance. So going back to the Trivia QA example, you can see that generally the performance is a bit better when providing examples in context. Okay. So yeah, sorry, go ahead. Is there a question or? Okay. So I'll just quickly mention as an aside that it is possible to get mass language models to work in this way, in this few-shot and context learning setting. This is an example of how you might do that with the T5 family of models. Basically, you feed in the prompt, the request, you feed in the input-output examples, and then for the example that you want to generate a prediction for, you mask out, you basically insert a mask token at the end of the input, and then you take the first token predicted by the model, add it back to the input, and then add a mask token at the end of that, and see the first token the model predicts, and do this continually until you get a complete output. But this is a kind of an expensive way to do it, so we won't talk about this in detail. So in the work that I'll talk about now, our main goal was to explore whether this fine-tuning paradigm that GPT-3 was trying to move away from is actually a promising way to perform few-shot learning. And in particular, we focused on a paradigm for fine-tuning called parameter-efficient fine-tuning, where the goal is to get the model to do a new thing while only adding or updating a very small number of parameters. Okay, so as I won't go into a lot of detail about the different methods that people use for parameter efficient fine tuning, although a bunch of them are listed on the bottom right there. I'll just only say that in this paper, we introduced a new parameter efficient fine tuning method called IA3 that basically takes the inner activations in the model in a few different places and introduces a learned vector that's multiplied element-wise by those activations. And ultimately, at least in the few shot setting, what IA3 allows you to do is get comparable or better performance to fine-tuning all of the model's parameters while only updating the equivalent of about 0.01% of the model's parameters. Okay. So now we have this technique that is as effective as full model fine-tuning in the few shot setting, but only updates a very small number of parameters. So now let's try to compare this in terms of the costs to few shot and context learning. So if we take our parameter efficient fine-tuning method I just mentioned and apply it to T0, then we call that T-few. And that's the costs of T-few are shown in the top row here. Now we can compare that to the cost of using T0 as well as the LM adapted T5 model I mentioned previously, and using few shot and context learning, as well as the cost of doing few shot and context learning with 3 GPT-3 variants shown here. And this is on a set of tasks from the GPT-3 paper using the same number of shots that they consider. And the key thing here is that after fine-tuning, T-few, because it's a fine-tuned version of T0, has the same number of inference flops as T0. And that is a dramatically lower cost in terms of the flops at inference time than few shot and context learning, because in few shot and context learning, every time you make a prediction, you have to process all of the in-context examples. And if there are a lot of in-context examples, or they involve very long inputs and outputs, that can involve processing a lot of tokens, which in turn makes the inference cost very high. Okay. Now the difference here is that when doing fine tuning with T-few, you do incur some flops during training. And so if you look at the second column, things look pretty dark for T-few. However, the total training flops listed here is only about 20 times more than the inference flops for one example with GPT-3. So what that means is that by the time you've processed 20 examples with few shot and context learning with GPT-3, with the largest variant of GPT-3, you already could have completed training with T-few. And now if you look in the left column again, the inference cost for a single example with T-few is about 1,000 times cheaper than an inference cost for the largest GPT-3 variant. So if you pay a little bit of cost for training, you end up being about 1,000 times faster at test time. Now, the other disadvantage is that because you have to save parameters, you end up incurring like a disk space cost. But because you're updating so few parameters, you only need to store about 4 megabytes of parameters on disk, which, for most people is not a significant amount of disk space. Okay, so if we then compare the flops per inference example versus the accuracy for T-few, T0, the LM adapted T5, and the 3 GPT-3 variants I mentioned, where the dark blue points in this plot are for few shot and context learning, the green points are Zeroshot, and the gold star is for T-few, which does parameter efficient fine tuning. You can see that T-few not only gets dramatically better performance than the best GPT-3 result, but is also, as I mentioned, about 1,000 times cheaper. Now, to make sure that this approach works kind of on real world tasks, we evaluated T-few on Raft, which is a benchmark where training sets are provided with only a few dozen labeled data points, and there's no validation set, and the test sets are completely hidden. If we apply our T-few recipe to the Raft benchmark, we ultimately outperform the human baseline for the first time and outperform the next best method by a significant margin. So this paper hopefully provides some compelling arguments that rather than doing few shot and context learning, you should do parameter efficient few shot fine tuning. Okay, so the last piece of work and the last kind of thing that people want to do with language models that I'll discuss is training the language model to learn stuff, learn facts, okay? And so I'll return to Trivia QA for the third time, looking at the results from the GPT-3 paper. And again, the performance with few shot learning was a bit better than zero shot. But as I mentioned before, in both cases, the largest model underperformed human evaluation by a decent amount. But this also provides somewhat of an unclear, incomplete picture, because we're looking at the average performance across a very wide variety of facts, very well-known facts, kind of more esoteric knowledge. So one way to kind of break down this performance in a more granular way is to ask, does the model do better on facts that it was exposed to many times during pre-training? So this kind of goes back to the question from way earlier in the talk as to whether the language model is better at performing tasks that it saw implicitly during pre-training. Now let's ask the question, is the language model better at learning things that, learning facts that it was exposed to during pre-training more frequently? And of course, as you might expect, the answer is yes. So if we look at the performance of Bloom rather than GPT-3 on Trivia QA, and we separate out the performance of the model in accordance to, basically we split the validations or the test set in accordance to the number of times the fact that the question was focused on appears in the pre-training data, you can see this very reliable behavior where the model gets better at answering questions about facts that it was frequently exposed to during pre-training. But now you're probably wondering, how did we determine the number of times that a fact appeared in the pre-training data? Well, we built the pipeline that's diagrammed on the screen here. The basic idea is that we look at the pre-training documents, we apply a basic entity linker to them, and we look at the question answering examples and we apply an entity linker to the question and the answer. And for a given question answer pair, we now have in a loose sense, what entity is this question about and what entity is the answer to the question. And to identify relevant documents, we basically just look at documents where the question entity and the answer entity occur. So this is a little bit of a noisy process. So to kind of sanity check that it makes sense, we looked at, and I apologize that it looks like the x-axis labels got cut off here. This is just the same scale on the x-axis that we saw before. If we train a language model and we on a normal unperturbed data set, and then we take that data set and we delete a bunch of relevant documents from it for certain questions, and we compare the original model's performance to the model with the documents deleted on the questions that we deleted relevant documents for, you can see that for questions about very rare entities on the left, the performance is not that different. But for more common entities, we do see this big gap in performance that suggests that deleting those relevant documents actually does impact the model's ability to answer questions. So this is not purely correlational. There is at least some causation here. So now an interesting question to ask is basically, if we look at the model's accuracy across a number of scales, can we extrapolate the performance of the model for different buckets, and where the bucket is basically how frequent are the facts for the questions in this bucket. So if we look at the bucket for the questions about very esoteric knowledge, questions about things that were a relevant document, there were very few relevant documents in the pre-training data set. And then we actually found a very, very strong linear fit, at least when using a logarithmic scale in the parameter count, which allows us to basically extrapolate and say, how many parameters would I need in order to have a model that performed at human accuracy on very rare questions? And you can see here, this is for Bloom. So the largest model with 176 billion parameters is the furthest blue point to the right. We would need to scale up by many, many orders of magnitude in order to reach human performance on very rare questions, or questions about very rare facts, rather. And so one simple way to get around this issue is to think about whether providing relevant context in the model's input allows it to answer questions better. And this is similar to retrieval augmented models. It's a common approach, so that we're not innovating in any way here. But it we were interested in performing this analysis for models that did retrieve relevant documents from the pre-training data set and basically were forced to answer a question about the document itself. So this is more like a reading comprehension task. And you can see here that if we use and in this case, we're using a very basic retrieval mechanism. We're just using the BM25 algorithm, which is just a simple text overlap based search algorithm. And we retrieve a few relevant documents from the pre-training corpus and feed it into the model for each particular question. We see much less of a dependence on the number of relevant documents in terms of question answering capabilities. And in fact, we kind of see the opposite trend. The model is now better at answering questions about esoteric knowledge. And so why that might be, well, the guess is that if there are more possibly relevant documents, then the model the BM25 algorithm might have trouble finding a relevant document. And in addition, relevant documents probably also are longer for well-known entities, for kind of well-known things. So it might be harder to do reading comprehension on much larger documents. So, but beyond that, we've at least removed, if not reversed, the trend that we saw earlier. So that's all I'm going to talk about now. I've kind of just raced through a bunch of papers that hopefully suggest new avenues for building better language models. I'm happy to provide references for any of the papers that I mentioned offline. And also, whenever I give talks, I try to ask for anonymous feedback. If you have any anonymous feedback for me, maybe I talked too fast, too slow, gave too much detail or too little detail or whatever, you can use this link on the screen here to give me anonymous feedback. But yeah, I'll stop talking now and happy to answer any questions.